Yeah, so hello and welcome to the third workshop of ComNet. I and Iga Jatin will be presenting to you. So the in the workshop we will be discussing about channel encoding. Then we will be discussing about modulation. Then about various characteristics of channel. Then in the end we will have a short hands-on of MATLAB. In the last workshop, we talked about how source signal is converted to a message via various schemes such as Huffman code, uh, and that is further sent to channel encoding. So in this workshop, we will be talking about the boxes which are written in green. And by doing this, we can basically we have basically covered the whole process. That is, after transmitting the signal from source, we can simulate all the things and get the final output on the at receiver.
Sir,
Yeah.
sir, is channel just a medium in which sources are sent?
Yeah, so in channel we send the signal uh, that is called channel. So what happens is we send a lot of signals in the channel. So a lot of signals leads to noise. So we have to take care of that. So that thing we will discuss in channel part. So channel is basically a medium. So in wireless communication, like mobile phone, we have air. In like broadband, there is optical fiber. So in that, the medium is, the thing between that glass covering. So that is the medium. So that is also channel. So in electricity, we can say the copper wires, they are the channel. So channel is basically
Okay,
medium
sir.
used to transmit information.
Yes, sir. Thank you.
So channel encoding. So first thing is we after the information that we get from the source has been converted to bits, we have to add some extra bits to ensure that we can decide if the encoding on receiving the bits at the receiver, we have to decide if the uh, transmission has been done correctly. So for that, we add some extra bits uh, for error detection. These bits are redundant, so they are not actually providing any information, but they are used to see if the transmission has been done properly. So these are the common types. There are two things. One is error correction and error detection. So in correction, today we will be discussing about ARQ and FEC. And in error detection, we will be using about parity bits and CRC. Uh, So ARQ stands for automatic repeat request. So it basically means that when a sender sends a signal to the receiver has to send an acknowledgement back. If it does not receive the acknowledgement, the sender has to send the signal again. So this is ARQ. In FEC,
Sir,
huh?
sir, in ARQ, the signals keep sending, and if we don't get it back, is it continuous process?
Yeah, we keep on that there are various types of ARQ. So we can one thing we can do is we can send the data, then wait for acknowledgement. One thing we can do is do a window type. So like we can send 1 to 3, wait for acknowledgement. Then if we get acknowledgement for 2, 3, and we not did not get acknowledgement for 1, then we will transmit 1, 4, 5. So like that also we can do.
Sir, what if we don't get acknowledgement?
if we don't get acknowledgement, we will transmit the data again.
Okay, sir. Thank you.
The second thing is forward error correction. So in this, what we do is we take the input data and we expand it to multiple bits using some type of formula. So here what we see is the input is 1 bit and we are converting it to 3 bits. So like if we get a new bit inside, the previous 2 bits are stored in M0 and M-1. These are used to get 3 bits, N0, N1, N2, using the convolution. This is for convolution. So it is basically a XOR. So we take the XOR of M1, M0, M-1 every time. This is used to correct if we get any error, so we can correct the received bits also from this. So these are of two types: convolution codes and block codes. Next, we will move to error detection. So in day-to-day lives, mostly we use error detection schemes only and rely on acknowledgement for if to decide if we have to resend the data. So error detection is type is parity bits. It is very commonly used. So what basically we do is uh, we see we basically count the number of bits and see if they are even, if the number of set bits, that is bits with value 1 are even or odd. So what we do is we add an extra bit which is used to decide uh, like for example, if we write 101 and we have decided that we will use one parity bit. So parity bits, so in this case, the answer would be 0, as we have two already in the message. There are two one set bits which is even, so the extra bit will be 0. A very popular scheme is Hamming code. It is basically the most efficient way to uh, for to detect 1 bit error in the whole data. How it works is for like 0th bit, for all the indexing is done 1, 2, 3, 4, 5, 6. So if we write the values of this index in binary format, uh, from that we decide like this would be 1, this would be 1 0, this would be 1 1. So what D1 represents is it is the XOR of all the locations which have 1 in the 0th location. So here we can see D1 would be the XOR of uh, D1 would be XOR of 1, 3, 5, 7, 9 and 11. Similarly, D2 is the XOR of all the bits which have 1 on the second 2th position. Uh, so like this, we can basically decode by adding 4 parity bits. We can decode the whole whole message. Another popular use of parity bits is in Aruko markers. So these are very popularly used to detect the camera pose estimation and in AR. So how they work is this white strip is redundant. Inside this one, black is redundant. So if we so if this is a 5 cross yeah, so this is a 5 cross 5 Aruko marker. So in this, if we see black represents 0 and white represents 1. So 0 1 0 0 1. So if we check the parity bits here using Hamming code. So 1, 2, 1, 2, this one, and this one. So these are three parity bits, and if we see, so this is basically used to decode. So we can see there are three, only two data bits and three parity bits. So overall, the information provided by this whole ARCO marker is of 5 bits. Sorry, 10 bits. So by this is used to get the information from the ARCO marker. That is, so for 10 bits we can have 1024 ARCO markers. So that's how it's used. Next is CRC. It stands for cyclic redundancy check. So in this this is very popular. It is used in Ethernet packets. So it is because popular because it gives fixed length encoding. That is, whatever be the length of the message, the encoding that we will get will be a fixed length. So in this image, we can see that the length of the bits is 3 bits only. Length of the extra bits we are adding, so that is only 3, and the message signal is very huge. So even if we change one bit in the that is one bit gets corrupt during transmission, the CRC will change very much, and we will be able to detect any error. So this is how it happens. You can see this image. Basically, what is done is we take XOR again and again, and after that, in the end, there is one quantity that is left. Only in the right side. So that is the 3 bits that we transmit forward. You will find I have added in the references, I have added YouTube links for this. You can find that from there. So for next thing, Ega Jatin will present you.
Hope everyone can see my screen and hear my voice. Just confirm, Pranav.
Yeah.
Yeah. So let's get started, guys. We'll talk about modulation. So we will see what is modulation, why it is used in the communication, and what are the different types of modulations. So in a broad sense, communication is the exchange of information either wired or wireless. That is between 2 points which are far away from each other. So this information could be a voice signal or an email or some television signal. But here let's take an example of the voice signal. So if we consider the speech signal or the human voice, so it contains frequencies up to 3 kilohertz. So if we consider the entire audio spectrum, then it varies from 20 hertz to 20 kilohertz. So this low frequency or the message signal is known as a baseband signal. And if we want to transmit this message signal to the far distance, then we might have some challenges. So we'll talk about these challenges a little later. But the thing is, this baseband signal cannot be transmitted directly. So with the help of the high frequency periodic signal, it can be transmitted. So this high frequency periodic signal, which carries the baseband signal, is known as the carrier signal. But the question is how to impose this message of the on the baseband signal onto the carrier signal. So we know that any signal has 3 basic properties, that is amplitude, phase, and frequency. So the modulation is a process.
Sir.
Yeah.
Sir, if we mix one signal into another, don't other जो carrier signal था वो correct नहीं होगा?
We'll discuss it in the further. Okay, whatever you have doubts, keep it in the chat. We'll be discussing later in the last, so it will be clear. So once we go through all the topics, you would get a bigger clarity, bigger picture of this. Okay. So this, okay, what is modulation? So modulation is a process where one of these properties of the carrier signal, like amplitude or phase or frequencies, are changed according to the baseband signal. So based on the properties which are changed, there are types of modulations. Before we get into the types of modulations, let's see why this modulation is required. So the first reason would be the size of the antenna. So the size of antenna is proportional to the wavelength that is transmitted. So let's say the size of antenna is equal to lambda by 4, is proportional to lambda by 4. That is one of the reasons why we use modulation. So then the second reason is to reduce the interference. So let's just imagine in a single room there are 3 people talking to the same person. Then the person who is hearing it cannot hear anything because 3 people are talking at the same time, there is interference, right? So similarly, if there are 5 different voice signals which are around the same frequency range that are transmitted without any modulation through a single channel, okay, so then there will be the interference between them. At the receiver end, we won't get any transmitted signal, but instead, if each signal is modulated at a different carrier frequency and all the carrier frequencies are relatively far away from each other, then there won't be any interference and all the signals can be demodulated at the receiver end. So using this modulation, the interference can be reduced, and the second and in the same time, the multiplexing of the different signals is also possible. So the same example which I've talked to you earlier is the example of the frequency division multiplexing, where the different message signals are modulated at different carrier frequency, and because of that, they can be transmitted simultaneously. So there are some important aspects why modulation. So these are the important aspects why modulation is used in communication. So now let's see what are the types of modulations. So we have, so broadly speaking, we have analog modulation, digital modulation. So if the message signal is analog, then it is known as analog modulation, and similarly if the message signal is digital in form or in terms of zeros and ones, then it's known as digital modulation. So first of all, let's talk about analog modulation. So so based on the type of carrier signal, the analog can be further classified into 2 categories, that is continuous wave modulation and pulse modulation. If the carrier signal is continuous wave signal like sine wave signal, then it is known as continuous wave modulation. So on the other hand, if the carrier signal is in pulse signal, that is then it is known as pulse modulation. And first of all, let's see some different types of continuous wave modulations. So mainly there is amplitude modulation, frequency modulation, and phase modulation. So in this case, the amplitude modulation, the amplitude of the carrier wave changes according to the message signal. So if the message signal has high frequency signal and the carrier signal, then the amplitude modulated wave would look like this. So as you can see over here, the shape of the carrier wave changes according to the message signal. Similarly, in the case of frequency modulation, the frequency of the carrier wave changes according to the message signal. So with this increase in the amplitude of the message signal, the frequency of the modulated signal will also increase. Similarly, with the reduction of the amplitude, the frequency of the modulated will also reduce. So in the same and similarly, now in the case of phase modulation, the phase modulation signal changes according to the message signal. Now we will see what different types of pulse modulations. So there are mainly 4 types of modulation techniques. So that is pulse amplitude modulation, pulse width modulation, pulse position modulation, and then is pulse code modulation. Now we'll briefly we'll look into each modulation techniques. So in this modulation technique, the message signal is in analog in nature, while the carrier signal is in pulse train or finite frequency. So in the case of pulse amplitude modulation, the width or the duration of the pulse will remain the same, but the height or the amplitude of the pulse signal will change according to the message signal. Similarly, in the case of pulse width modulation, the height of the amplitude of the amplitude of the pulse will remain same, but the width of the pulse will change according to the message signal. So here the message signal amplitude is sampled at the rising edge of each pulse, and the width of the modulated signal is proportional to the sampled amplitude. Similarly, in case of pulse position modulation, the width and the amplitude of the pulse will remain fixed or same, but the position of the modulated signal will change according to the input signal. So at each rising edge, the message signal is sampled, and based on the amplitude of the input signal we have, the position of the modulated signal will change. As you can see in the graph, you would easily understand. So let me tell you. So that means as the amplitude of the input signal increases, then the modulated pulse will further go away from the reference point. Okay. So in fact, it will be generated with the help of pulse width modulation technique. So that means by generating the pulse at every falling edge of the pulse with the modulation signal, the pulse position modulation can be generated. All right, now let's move on to the next modulation, that is pulse code modulation. So in the pulse code modulation, the message signal is sampled at a finite interval, and the sample value is quantized using the quantization process, which we have earlier discussed. Then using the analog to digital converter, the message signal is encoded, and then we have that modulated signal. All right, so far we have seen the different types of analog modulation techniques. Okay, now the message signal was in analog in nature. Similarly, let's now talk about the digital modulation techniques. So in a broad sense, mainly there are three different techniques, that is amplitude shift keying, phase shift keying, and frequency shift keying. So in all these digital modulation schemes, the message signal is in the digital form. So now it's time to understand what is digital modulation, and then we'll discuss why digital. So digital modulation is a special kind of modulation where the message signal is in digital nature. It may be in binary or MRA encoded versions. So the carrier wave, if the carrier wave is of analog nature, so we can so you can understand here that the analog kind of modulation where it examples are FM, AM, and PM modulation techniques we have seen earlier, where we have sinusoidal wave carrier. So in digital modulation case, we have analog carrier wave, but the difference between analog and digital modulation is based upon the message signal. That is, the modulating signal is in analog form is in analog nature for analog modulation, whereas in digital form for digital modulation. So this modulation signal is okay. Now let's So now let's talk about in digital modulation, what this modulation technique is known as is like keying or switching. What we see is an amplitude shift keying or switching. So this shifting or keying is known as modulation. The ASK, PSK, FSK are analogous to AM, PM, and FM respectively, as I've already told you. The difference is that digital modulation techniques and the modulated signals are in digital nature, while in analog modulation, the techniques are in AM, FM, and PM. So the amplitude shift keying, ASK in short, is the amplitude of the wave carrier, which is analog in nature and is changed, or we can say switched, according to the digital input signal. Since we know that the modulating signal here is in digital form, therefore ASK is analogous to AM. So AM is a kind of analog modulation and in amplitude modulation also we vary the amplitude of the carrier wave according to the instantaneous value of the message signal. So the the difference is only of the message signal in nature, where in digital where it is in digital in nature. So we switch the amplitude of the carrier wave according to the digital input signal. So let's understand this with a very simple example. So here we have 10110 as the data. So this is an input, this is a digital input signal. As I've told you, the message signal. The modulating signal is in digital nature. So this is a binary digital nature. So and this is the carrier wave. We know that the carrier wave is sinusoidal. That is analog in nature, like the analog modulation. So here the modulating signal is digital and the carrier wave is is analog. Now we want to change the amplitude of the carrier wave according to the binary sequence, according to the digital binary signal we have. So what we do in amplitude shift keying is we do not transmit any kind of signal when we have 0, and when it is 1, then the carrier wave is transmitted. So as you can see here that the places where it is 0, it is clear from the example that the other 3 places, that is the first and third and fourth, we have modulated signal, and at 0 places we don't see any kind of signal passing through the modulated signal. So now we'll get into FSK. FSK. So here in the frequency shift keying, if the frequency of the sinusoidal carrier wave is varied or switched depending on the digital input signal, then it is known as frequency shift keying. It is analogous to FM, frequency modulation, which is a type of analog frequency. Since the frequency modulation, which is analog of type, we just change the frequency of the carrier wave according to the instantaneous value of the modulating signal. So in this case, we also see in this case also only the difference of modulating signal, which is in digital nature, and so we can change the frequency of the sinusoidal carrier wave, or it is switched according to the digital input signal. So this is an example. So this is the concept of how the FSK takes place through the process of so this is a small example of FSK where one is transmitted with when one is transmitted when we have a high frequency of the carrier wave. Okay, so since it is a frequency shift keying, therefore as per the digital input signal, that is either 0 or 1, either 1 is transmitted, we will be changing the frequency of this carrier wave according to the digital input data we have. So the frequency is reduced when we have 0, and when we have and it will be increased when we have 1. We know what is frequency, right? Frequency is the number of cycles that are passed in 1 second. So it is higher when 1 is transmitted and lower at 0 is transmitted. So now let's see what is PSK, phase shift keying. The phase shift keying of the carrier wave, which is analog, is switched as per the input signal, input digital signal. This is analogous to phase modulation. So the concept is the same as before, as in phase modulation. The phase of a carrier wave is varied according to the instantaneous values of the message modulating signal. So in this case, also since it is just digital kind of modulation, the sequence that input signal is of digital nature, and the carrier wave is varied or switched according to this input digital signal. So let's understand the concept with the help of this beautiful waveform. So here we have this digital input 1, 0, and 1, and this is the carrier wave analog in nature. So now we want to perform this phase shift keying. So since we'll vary the phase of the carrier wave Here, according to the digital input signal, so whenever there is a change in the input signal, that is here it is changing from 0 to 1, and at that place there is a change in the, or when there is a change from 1 to 0 also, so we can see there is a change of the phase shift of pi, that is 180 degrees, takes place in the phase modulation. So let's understand it, how it takes place with an example here. Here it is 1, so there is no change in the start of the waveform and the carrier wave is transmitted, and at this place it changes from 1 to 0. The digital data, we have 0, the next following is 0. So there is a phase, we can see a phase shift taking place, that is it is changing by 180 degrees. Before the wave was going upwards, now it changes to by 180 degrees and goes down again. So this is what we observe in phase shift keying, and we see that PSK uses two phases, that is 0 and 180 degrees, and has one bit. So this is also known as BPSK, that is binary phase shift keying. Before we see into other modulation techniques, we'll once see the three modulation techniques we have discussed: ASK, FSK, and PSK, and how the waveforms vary, how the waveforms are modulated through these three methods. Now let's see what are coherent and non-coherent detection systems before we get into the other parts of modulating techniques. So a coherent system needs information regarding the carrier phase at the receiver end, so that they can detect and decide whether the data sent is from the receiver end. Whereas the non-coherent system does not need any kind of carrier phase information, that is at what angle does the receiver sending the message from. So it can be retrieved without any carrier phase information. So now coming into QPSK, that is quadrature phase shift keying. Now this is a form of PSK in which two bits are modulated at once. So before we saw binary phase shift keying where we modulate one bit at once, and here we are going to do we'll be going 2 bits at once. So this is the difference between BPSK and QPSK. Now it can select one of the possible carrier phases from 0 degrees or 90 degrees or 180 degrees or 270 degrees. So out of the 4 phases, it will select any one of the phase in the carrier. QPSK allows the signal to carry twice as much as information as the original PSK using the same bandwidth. So here we can increase the data rate as it will carry twice the amount of information than the BPSK. As BPSK uses only 2 phase shifts, but rather here the QPSK uses 4 possible phase shift keys, that are 4 angles. So bandwidth can be saved over a period over this method by increasing the data rate. QPSK is used in the modern cellular phone systems and cable modems, and in the transmission for satellite transmission for MPEG videos. Before we see the waveform, what you need to keep in mind, is the bottom right table you're seeing. You need to follow the rules to modulate this QPSK waveform bit by bit. So as you see, there is a 0 0 1 0 1 and 1 0 and 1 1. So the waveform 0 0, we have a waveform going from a modulated signal, but 1 0, what you see is there should be a shift of 5 pi by 4. So now the waveform, we can see the shift of 5 pi by 4 from the previous waveform, and the next bit is 0 1. See from the table 0 1, we have there should be a 3 pi by 4 phase difference. So from the carrier wave, the previous wave signal, so now there is a phase shift of 3 pi by 4 and so on. So whatever information modulated signal, we need to take this table as a reference for calculating the data, modulating the data. Now coming to DPSK, differential phase shift keying. It is not possible to have a non-coherent detection of PSK. As you need phase information. So that is the reason we use DPSK for non-coherent detections. And we have seen that what non-coherent systems are have already discussed to you. So this DPSK also helps us in reducing the cost of circuits. Now let's see what happens through the modulation to the carrier waveform. As we look into the waveform below, let's understand how the waveforms, DPSK waveforms are generated. The important point what you need to keep in mind is if the next data is 1, there is a change in the polarity of the output. If the next data is 0, then we don't change the polarity of the output signal. So as you can see, the first data is 0 and the next is also 0. We don't see any difference in the polarity of the wave signal. Then the third data is 1. So we can see that there is a change in the polarity of the waveform, and followed by the next data is also 1. So there is a polarity change again in the wave signal. But the next is 0, the waveform carries the same polarity, and so on. You will observe this circuit. Okay, so this is how differential phase shifting happens in the waveform. Now, and you will observe the circuit complexity is to be less, but what we don't as we don't have any oscillatory circuits, but the drawback of this technique would be it will be a little noisy. So going on to quadrature amplitude modulation, that is QAM. So it is the most common modulation modern digital used in these are used in modern radios. This is used to encode information onto the radio frequency waves. With amplitude modulation, a simple on-off key switch is used is enough to encode zeros and ones. With frequency modulation, signals with two different frequencies do the job. That is, there is a phase shift key of phase shifting of 180 degrees does this trick. But QAM modulation, this is a combination of amplitude and phase modulation. At the input of the QAM modulator is the digital data processed by symbols, that is zeros and ones, or a group of bits at once. At the other end, the input of the modulator is the RF carrier wave, radio frequency carrier wave. These input signals are combined in modulator, which controls the amplitude and the phase of resulting output signal, which that does encode more information onto the signal compared to any modulation alone. So the length of the symbol is determined by QAM modulation depth and maximum number of symbols. And if symbol is 01, QPSK symbol is 0001, 16 QAM is used. If it is 001011, 64 QAM is used. The symbols can be mapped into a so-called constellation diagram, so which helps us understand the QAM modulation much easier. See, as you can see, QPSK uses 2 bits per symbol, whereas QAM uses 16 bits per symbol, and 64 QAM uses 64 bits per symbol, and so on. Because of the noise transmitted, the signal fluctuates around the ideal value. So the noise limit of a QAM is given by the depth and is given by a point where the acceptable noise levels area for each symbol when start to overlap. So in the right image, you can see when the radio signal starts to overlap, there is overlapping causes errors. So with the growing QAM depth, we pack more information into the same signal and also shrink the space between the symbols, which are naturally decrease the acceptancy of acceptable noise level. So this is the reason why high MC. So this is why we use QAM over modern techniques. So now this is a constellation signal for 16 QAM modulation. Now coming to over modulation. So over modulation is a condition when when the instantaneous level of modulated signal exceeds the value necessary to produce the 100% modulation of the carrier. So in the sense of definition, it is almost always considered a fault condition, or in layman terms, it is called we can say the signal is going off the scale. So over modulation results in superior emission of the modulated carrier, uh, and distortion of the recovered modulation signal. That is means this means the envelope of output waveform is distorted. As you can see in the third image, you start to see distortion in middle of the waveform. So that happens because of the over modulation. Although over modulation is sometimes considered to be permissible, and it should not occur in the practice, a distorted waveform envelopes will result in distorted output, as you can see in the third image. Okay, Pranab, I give it to you now. Pranab,
Yeah, just
yeah,
a
yeah,
sec.
yeah, yeah. So
So does anyone have any doubt until now? So okay, let's carry on. So channel is basically a medium through which we get through the message to the audience. There are today we are going to discuss about channel, these topics about channel. So fading, which includes reflection, diffraction, scattering. Then there is noise. Usually to model the noise, we use the OG, and we will discuss what it is. And there is channel capacity theorem. So it basically tells the maximum capacity that we can get from a channel. So all the theory, all the algorithms that we design, we are trying to achieve this accuracy. Uh, so it is the proof is very complicated for it. We are only going to discuss the theorem. Interference. So interference is when the other signals having the same frequency uh, uh, other signals having the same frequency, they disturb the amplitude of the signal. So for this, we design the waveforms and change the carrier frequency to ensure that no two signals have the same frequency. Then the thing is frequency and time domain multiplexing. So if we start dividing the frequency, there will be very less frequency available to uh, ensure proper communication. So what we do is this is the technique which is commonly used to ensure the maximum efficient usage of the bandwidth and the time. So let's start with fading. So fading is basically when the signal travels through a medium, it loses some energy. So each medium we can see has a channel, has a characteristic. So this HF that we are seeing, it is the characteristic of the channel. So it tells what like how much it will allow. So we can see that the channel bandwidth, we can see that if the frequency is higher than this value, the channel will not allow it to pass. And if the frequency is within these value range, then the frequency will be passed, and the variation in the frequency will be as shown in by the blue line. Uh, so this is very important. So basically we model what the channel will look like using HF, and the final output that we get is represented as a multiplication of both. So the output is equal to HF into XF. Then there is noise. So noise is that the unwanted interference that we get, which corrupts the signal. So it is kind of random. So we use organ. This is organ. So organ stands for additive white Gaussian noise. So additive stands for because it is added to the normal signal. So additive. White stands for because it has uniform power across all frequency band. So what this means is that if we calculate the power, that is integration of absolute of amplitude square over time. So we get the power. Power is basically amplitude square. So if we calculate that, it is uniform across all frequency. So noise contains the components of all frequencies. Then there is Gaussian. Gaussian is it is normal distribution. It tells the probability of getting an amplitude. So this is how a Gaussian curve looks like. And above we have the probability. So what it says is that having the noise at 0 is maximum. And as we increase the amplitude of noise, its probability will keep on decreasing. And the area of under this curve is 1. So this is basically normal distribution. And we use this to calculate organ noise. And this is the power spectral density, which is constant at n naught by 2 throughout all frequencies. The next thing is channel capacity theorem. So it basically dictates what is the maximum channel capacity, that is bits per second we can achieve. Uh, this is the formula. B is the bandwidth, 1 plus S by N. S is the power of the bits, signal power, and N is the noise power. So we can see that if we increase the signal power, then the channel capacity will increase. And if we increase the noise power, the channel capacity will decrease. And if we increase the bandwidth, the channel capacity increases. So also, like if we keep on increasing the like so this is like the maximum we can achieve from this. The next thing is interference. So interference is the phenomenon where multiple signals superimpose to get a resultant signal of a different amplitude. So it basically destroys the original signal. So if we below I have written the criteria for zero ISI. So what it says is I have also put a link to this video in the references, but in brief, I would say what it says is that whenever we make a sample, the amplitude should be 1. Uh, Otherwise, the amplitude from the signal that we are taking should be 1. For other signals should be 0. So basically no other signal should be interfering with the current signal. So So this is the demonstration basically. So we take sample at TB, 2 TB, 3 TB, and what we want is, and this is the pulse that we are sending YT, square pulse. So what we want is that the other pulses should not interfere with the previous or the next output in frequency domain. This one is in time domain and the figure on the right is in frequency domain. So they should not interfere with each other. I will, you can see the video. There are we talked about, so like we can't transmit the square pulse directly because square pulse has infinite bandwidth and we can't use it. We will get a lot of interference then. So what we do is we use a sine C curve. So we multiply the square with the sine C to get the final output. This is the sine C curve. Uh, so if we calculate the Fourier transform of this, it is a square pulse. Uh, this is on this blue line on the right is the square pulse. So if we calculate the Fourier transform of this, we will get a square pulse. So we can see a signal which is infinite in time domain. We get a square pulse in frequency domain, limited bandwidth in frequency domain. And this rule applies vice versa also, like if the frequency bandwidth is unlimited, then the if we calculate Fourier inverse, then it would be also band limited. Yes, Drew, do you want to say anything?
No, Bhaiya, sorry. Uh, Raised my hand by mistake.
Okay. So raised cosine is another curve that we use for this. So raised cosine is basically the other lines that you see, this green one, this pink and red one. So these are the raised cosine curves. So their formula is defined and then we calculate their pulse in time domain. It looks somewhat like sine C curve, but the decay is very fast. So sine C curve takes a lot of time to decay to a zero. The raised cosine curve decays fast, but it takes a more bandwidth. So it is a trade-off, I would say. Frequency and time domain multiplexing, it is used to get the most efficient transmission. So we divide all the time and frequency uh, while transmitting. FDM stands for frequency division multiplexing and TDM stands for time division multiplexing. So to summarize, we have a channel. Channel is basically the bandwidth range. So like 5 kilohertz, we can say. So we use a mux. While transmitting, we divide the channel into a lot of parts, and we transmit it to the channel, and then it is decoded on the other side. So this is basically division of the frequency into a lot of channels, and each channel is taking a different message. In TDM, what we do is we take a whole message and transmit it in time. So a frame is used. So together we combine it and transmit it uh, using the same frequency, but what we do is we divide it into time. So this is the diagram basically in time and in frequency. So we here the on the left side we see that in frequency it is divided. Then all in the time domain, we see that too is divided in time into packets. So both we are doing. So in frequency also we divide, and in time domain also we make slot 0, slot 1. So this image that I have taken, it is from 4G. So in 4G, while transmitting from the mobile tower to the mobile device, uh, the signal looks something like this. uh, and it what the signal that we send from the mobile device to the antenna, the transmitter tower, that looks like this. So the difference between both of them is there is no frequency in the right. The channel is not divided in frequency. So the whole message is divided into time only. So this is why we do is because the method on the left, it takes a lot of energy to, and lot of the hardware is very huge to achieve this. But on the mobile device, we want to increase the battery life, and for that we use this. We do only we divide the signal only in time. These are some extra resources with some references. Uh, and in the next workshop, we will be discussing about OSI model, and we will discuss the last year's PS. Uh, so in the starting, so there is one thing like in the starting we discussed about CRC. So you have to implement the CRC in MATLAB using your code. You can, I will share the video links and the detailed assignment. Uh, there is a deadline of a week starting today, starting tomorrow. And you have to submit it, submit the MATLAB code along with the results as it would be specified in the PS. You can ask your doubts in the WhatsApp group or the Discord. Now we will go on to hands-on. I will be showing you the hands-on in both MATLAB and Octave. Octave version is less intuitive, so we will be discussing in the MATLAB mostly, and then in the last I will show how to run the file in MATLAB in Octave. Today we will be discussing about how to simulate BPSK, binary phase shift keying, QAM, quadrature amplitude multiplexing, quadrature amplitude modulation, and QPSK, quadrature phase shift keying. So in binary phase shift keying is what we do is we change the amplitude based on the bit. So if the bit is 0, for example, if the bit is 0, we transmit cos 2 pi fc plus t. And if the bit is sorry, the code files I have uploaded on the Teams, and I have also sent them in the chat. You can take a look at them. You can download them, and you can, if you want, implement now and see if you face any doubt. So what we do is we for 1 and 0, we convert that to 1 and -1, and then we transmit that signal. So these are the outputs. So we take a message signal 0, 1, 0, 0, 1, 1, 1, 0, and we convert zeros to -1. Then what we do is we make samples. So what we are trying to do is we send the same signal again and again. A lot of time in time we send the same signal again and again. So at t equal to 0.1 to 0.2, we are sending the same signal. As on the graph on the right, you can see from 0 to 0.1, we are sending -1, 0.1 to 0.2, we are sending +1. So to achieve that, we have to create a sample. So in the first workshop, we discussed that the analog signal is infinite, has infinite information, whereas the digital signal has a limited signal. So what we are doing here is we are converting a digital signal to analog signal. We repeat the same signal so many times that it approximately becomes an analog signal. So this is the constellation diagram. So most of the signals we can see are near -1 or +1. Then there is a frequency fc, and we multiply it by into cos 2 pi fct. This is the carrier signal. So what multiplying does is it changes the frequency of the input signal, the message signal, to fc. So this is how the message signal looks like. Then we this organ function in MATLAB. This takes two argument. It takes the modulated signal and the 10. 10 is basically the dB. 10 is the you can say that the energy of the noise signal. So if we increase 10 to very high, this noise that you are seeing in the signal, it will increase very much. Let me show you the modulated signal also. So what is happening is the FC and the T that we have taken, they are very close. So what is basically happening is cos 2 pi FC is always 1 on all the samples that we are taking. So in these cases, what we have to do is we have to either decrease the so what we can see is FC is varying in time. If now we modulate, so this is the message signal. It is varying very much in time. So this is of no use. So this is important while if we are going to choose a carrier frequency. Next, we move on to demodulation. There are for demodulation, we multiply the input signal, the received signal into cos to pi fct. So what this does is like the signal that we sent was empty, star cos to pi fct. So if we multiply cos to pi fct again, what we will get is empty, and changing cos to pi fct to the formula 1 minus cos 2x by 2. One plus cos 2x. This is the signal that we are in D mode. So we can see that the frequency of it has two components. Empty, it is a low pass signal, and empty into cos 4 pi fct, it is a high pass signal. So to remove the high pass signal, we uh, do convolution with the low pass filter. So this is the code for it. So convolution and demod and the low pass filter. So after that this is the demodulated signal. Uh, so this is the receiver constellation. So what it means is we in communication terms we use the word constellation a lot. So what it means is mapping the signal in a graph. Uh, this is very important to see how to make decisions. So let me just tell, like in the diagram for QAM, here we can see it has been plotted in amplitude, and like if we get if we receive a signal, then we decide what it means. We basically see which dot it is closest to. So let's say if we get a signal in the first quadrant somewhere here, so it is closest to 0101. So this value used to decide what output bit we are receiving. So constellation is usually used to represent how the received signal is mapped onto a signal space. So we talked about signal space in a second workshop. Continuing demodulation, after taking the convolution, we basically have the empty. So you can see that because of the noise and low pass filter, we we have like the signal is not perfect. Like we sent this signal, and what we are getting is this. So basically what we are doing is we are taking the output at the center. So this is one bit, second bit, third bit, and what we are doing is we are taking the output at the center here. At time, let's say 0.5, we are taking the output. If it is greater than 0, then we are saying that the output is 1. And if it is less than 0, then we are saying the output is 0. So by doing this, we have reconstructed the message bit. So this M reconstructed is same as what we sent before. So this is the whole cycle. So we send the signal, increased it time. Then after created a lot of samples in time, then basically digital to analog converter. Then we multiplied it with the carrier frequency modulation. Then we did this is the channel part. So to mathematically simulate it, we use organ. Then the demodulation. Then the low pass filter. This comes under demodulation only. Then we are basically reconstructing the previous signal. So the other things that we add in it is the parity bits part or the CRC part that also can be added in this. And what will happen is after reconstructing the M, we will check if the CRC is correct. So if it is correct, then we can decide that the signal has been transmitted in the right manner, or otherwise we will have to we will center NAC, no acknowledgement. So the transmitter will transmit the signal again. Next thing is QAM, quadrature amplitude multiplexing. So if anyone has any doubt until now. Okay, so moving on, QAM is quadrature amplitude multiplexing. So quadrature means 4 and amplitude means we are changing the amplitude. So what we do here is there is this diagram you can see. This is the constellation. So it is like BPSK. So we will BPSK is it is used to transmit 1 bit. So but in QAM we can transmit 2 bits in the same space. In the same frequency, at the same frequency, we can transmit 2 bits. For that, QAM is used. In this, we have to use 2 ways. One is sine and cosine. So what we do is we have a message like M1 and M2, and what is actually happens is there is one message bit and the bits at even places and the bits at odd places are used to make 2 messages. And same thing, we sample it in time, but like make all the 0 bits -1, sample it in time. This is the constellation. Then multiply one signal with cos and multiply second signal with sine. Then we add both the signals, sine and cosine. For received, we add the noise to the modulated signal. Then to retrieve the signals, we again multiply sine and cosine to the received signal. So again, using the simple trigonometry, you can get that if we multiply, uh, so uh, if we so here if we multiply sine and cosine, uh, we cannot extract, and after that if we use the low pass filter, what we will see is that only empty will be left, or empty in this case empty by 2 will be left in both the cases. So what we have done is in the same frequency range we have transmitted 2 bits. Here we are taking the low pass filter and then if it is greater than 0, then we say that the answer is 1, and if it is less than 0, then we say the answer is 0. Yeah, so this is the received signal. This is M deconstructed. So it is same as what we transmitted. So something that it is interesting here is the receiver constellation. So when we added noise to the modulated signal, we can see that all the dots in the receiver are telling where the signal is located. So we can see that a lot of noise has been added to the signal. Uh, on the right is what we transmitted, and on the left is what we received. Basically, to make a decision is not that easy. So which I will discuss in a minute. So next thing is quadrature phase shift gain. So in QAM, what we did was this was the constellation. So we were trying to map the bits on these 4 values. In QAM, QPSK, what we do is we map for 0, 0, let us say the signal is cos 2 pi fct plus 0 plus 5. Then the signal that we are the modulated signal that we are transmitting for 0, 1 will be cos 2 pi fct uh, 5 plus 90. For 1, 0 it would be cos 2 pi fct 5 plus 180, and 1, 1 it would be cos 2 pi fct 5 plus 270. So if I showed you the constellation diagram, it will look like this, and all the points will lie on the circle. This will be the equation that I was telling, cos 2 pi fct plus pi by 4, 2 pi by 4, 3 pi by 4, like that. There can be a phi also. This root 2es by ts is written to make the power of this signal 1. So here also, like, we are doing ME and M0, the even bits, and the M0 are the odd bits. 0, 0, we are the message signal is 0, 0, 0, 1, 1, 0, 1, 1. So we are divided into even bits and odd bits. 0, 0, dividing the message signal into many parts. These many parts are called symbols. I'm telling you these terminologies. If you read it online also, like, you would be able to understand what they're trying to say. So 0, 0 here in the message is the symbol, and that symbol is divided into the uh, uh, each symbol is treated differently. All the symbols are exclusive to each other. Uh, so the difference between QPSK and BPSK is that in QPSK, the bit error rate will be high. So, like, if the signal lies on the first quadrant or fourth quadrant, in BPSK case, we can easily say that the bit is 1. But in this case, if the region that the decision region that we are using has been decreased, so intuitively also we can say the bit error rate will be high. The procedure is exactly same as QAM because the equations that come in both the cases are same. This usually doesn't happen, but here the logic behind both of them is different, but the equations that come they are same. So in this case also, like, this is the message signal we divide it into even and odd parts. Then we create a lot of samples. Then we modulate it, create the final modulated wave. This is the received signal after adding some noise. Then the signal is we are trying to demodulate the signal, low pass filter, then the decision. Then after that we are reconstructing the previous signal. Like we are desampling. So if in the previous case we created a lot of sample. Now from the sample we are trying to decide which sample to take. So this is the reconstructed. So you can see that the final signal that we get is same as what we transmitted. So QPSK versus QM. So like you can see they both look same, but they have some differences. The spectral width of QPSK is wider than that of QM. QM has a lot of types, which are more efficient as compared to the other types of QPSK. So in QPSK, like if you want to divide this, let's say you want 8 PSK. QPSK code Q means quadrature. In 8 PSK there would be 8 types, 3 bits. So on this unit circle, you will make 8 points, and that would be the constellation. Mathematics would look somewhat like this only. That you can figure out based on the constellation how the mathematics will look like. In QM, what is done is this type of constellation is made, and based on each point is assigned a bit, like 000001. Then based on that bit, we calculate its amplitude and its angle, and that is used to calculate the transmitted signal. One fact, if you want to know about this, is like the bits change in like after 1 you don't see 2. This is because what they are trying to do is all the neighboring bits that we see, they are trying to keep them as close as the change in the neighboring bits. They are trying to keep them as close as possible. So this is gray code. So the constellation that we make is usually made in gray code. So the representation of 0 is 0, 1 is 1, but the representation of 2 is 0011 instead of 0010. Just a fun fact. So this is like in QAM there are 2 components, I and Q. I is in phase component, Q is the quadrature component, and A cos phi, A sin phi, and it is multiplied with this. This is somewhat how transmitter looks like. So based on the binary data, we calculate A cos phi and A sin phi. Then we multiply it with A cos pi, A cos 2 pi fct and A sin 2 pi fct, and then we add and subtract to get this thing. And then we transmit it through the channel, and after channel we do the split the signal, then again multiply it with A cos 2 pi fct and sin 2 pi fct, and again we can decode what the data we got. Uh, so like why we are writing the signal in these terms, there is also like a fact. So each signal that can be written in terms of I cos to pi fct and q sine to pi fct, it is a band pass signal, so band limited signal. So like in a frequency domain, that signal is band limited, so this is a standard that we use. So always when you will see in modulation schemes, they try to get to this thing, cos to pi fct and sine to pi fct, because this is a standard way of implementing a modulator. Like we take the carrier signal sine and cos component of the carrier signal and multiply it with the amplitude, a special amplitude for both of them, such that we get the desired output. There are a few YouTube links in the references. I would share them in the perfect order to you, so that you can understand all the concepts better. Uh, just a few minutes more, I will simulate the same thing in Octave also. So first you have to go to the folder. This is like the folder I am using. In that folder you have to type the like you can type a few words, then press tab, so it will automatically guess what you are trying to type. Then this is the .m file, and after writing that .m file, if you press enter in the command window, so all the graphs that we show in the MATLAB, that will start to come. These are the same thing as they were in the MATLAB. So you can see that it is difficult to see so many graphs in Octave. So to and the outputs are like this only. So what is done is, if we see this file, the code is huge. We can't debug and write all this code in the same time. So what is done is usually we divide this code into a few parts and make functions. So make a function and make a lot of files, and we decode each file one at a time, and we get the output from them. To verify the output one at a time, and then we combine those files together in the in the main file, and that main file is used to call all the other functions. So that is the better approach. So in the next workshop, we will be discussing the last year PS. So in that, this approach was very helpful while implementing the PS in Octave. We will discuss more about functions in the next workshop. That's all.